Okay, as we head into section 4.2 when we're discussing kinetic energy and the work energy theorem, you'll probably notice the first couple sections in this next unit are a bit of a review from grade 11 physics. And we just want to recall in this lesson the definition or what kinetic energy is. And remember that kinetic energy is the energy that an object has because of its motion. And we defined or symbolized kinetic energy using the capital E with a subscript K to represent kinetic energy. And we discussed, or you learned last year in grade 11 physics, that kinetic energy is given by 1/2 mv squared. And remember that our units for kinetic energy is the joule or joules with a capital letter J for short. Our SI unit for our mass is the kilogram. And we have speed, which is given in meters per second. And because we have speed, which is in meters per second, and remember work is a scalar quantity, this tells us as well that, kinetic energy is a scalar quantity as well. And let us begin this lesson just going right into an example. Why not? We have a car that has a mass of 2,155 kilograms, and again, I'm going to be a little bit more strict on our significant digits. We see here that the mass, which is 2,155 kilograms, has 4 significant digits. My speed of 22 meters per second has 2 significant digits. So when I calculate the kinetic energy of the car, as this question is asking us to find, I will make sure that my answer in the end has 2 significant digits. So following the equation, EK 1/2 mv squared, we can calculate that, easy substitution. And we get that our kinetic energy is 545,484.375. Those are all of our digits in the answer. When I plug this into my calculator, my answer needs to have 2 significant digits. So therefore, 540,000 joules of energy exists on the car. Okay. And that brings us nicely right into the work energy theorem. And how they are in fact related. The work energy theorem says that the total work done on an object by an external force equals the change in kinetic energy of the object. What we must assume in this case, this assumes no other forms of energy transformations. So we don't have any other form of energy transformation occurring, and that our applied force is constant. And throughout the whole energy unit, we're going to see a lot of this basic type of question come up. In this case, we are told that the total work done on an object is equal to the change in kinetic energy of an object. So our work is equal to our change in kinetic energy. So that tells you that work is equal to our final kinetic energy subtract my initial kinetic energy. So therefore, work is equal to 1/2 mvf squared minus 1/2 mvi squared. And we're going to use this concept quite a bit, and it's going to be shown more in elastic collisions, etc. And we're going to see right now a few examples of how we can use the work energy theorem in an actual problem. And in the first case, we have a car that has a mass of 2,135 kilograms. And it is traveling at 22 meters per second when it starts to speed up. So my initial speed is 22.5 meters per second. If 2.95 times 10 to the 5 joules of work is done, what is the car's final speed? So we are actually asked to solve for VF. So we know that work is equal to our change in kinetic energy. So work is 1/2 mvf squared minus 1/2 mvi squared, and it's the VF that I would like to solve for. Well, I noticed I have 1/2 going on. So that means I must multiply both sides of the equal sign by 2. That will get rid of the 1/2. And let's divide both sides of the equal sign now by m. So we have that 2w over m is equal to Vf squared minus Vi squared. Remembering we want to solve for Vf, our final speed. Therefore, bringing Vi squared over to the other side, we would have 2w over m plus Vi squared is Vf squared. Therefore, we can solve for my final speed by taking the square root of 2w over m plus Vi squared. So my final speed, after I substitute all of these numbers in and use a calculator to solve, we would see that my final speed would be equal to 27.9749. That's all significant digits included. My final answer must include 3 significant digits, so 27.9. I see that 7 is the following. Round up, so final speed is 28.0 meters per second. This decimal 0 is 3 significant digits. final example. What happens if I have a curler? Since the women's curling championship just finished, I believe the men's curling championship is now going on, I think. And that curling rock is 17 kilograms in mass and wants to travel 31 meters and then stop. If the coefficient of friction on the ice and the rock is 0.012, let's figure out our initial speed. So we have our curling rock. Best drawing that I can do there, although it looks a little bit more like an apple, but it's my best attempt. That tells me that we have a force of friction acting back on the rock in this case, and my displacement is in the positive direction. So my force and my displacement are in opposite directions. That tells you that work is going to be negative in this case, and let us calculate it. Well, first we need, what is our force of kinetic friction? That is calculated by mu k Fn, and remember, Fn is calculated by m multiplied by g. So that's going to be 0.012 multiplied by the mass of 17 and 9.81, giving you a force of 2.00124 for kinetic friction, again acting in the opposite direction, so negative. Therefore, work, which is force times distance, we'll take that previous answer and multiply it by the distance of 31, and that is an answer of negative 62.03844 newtons. Sorry, not newtons because this is work, this should be joules. What else are we given in this question? We have our mass. We have that it's coming to a stop, so your final speed is 0 meters per second. We want to know what that initial speed is. So, work, which is equal to the change in kinetic energy, which is 1/2 mvf squared minus 1/2 mvi squared. But you notice that my final speed is 0 meters per second. That gets rid of this whole term here. So we're left with work equals negative 1/2 mvi squared. So what does this give you? This gives us, let's solve for vi in this case. 2w, I also have to divide by m, is negative vi squared. How am I going to get rid of this negative? Because we cannot take the square root of a negative number. Well, notice that right now my vi is negative, and I have negative work as well. Two negatives will cancel each other out. So therefore, when I go to calculate vi, it'll be the square root of 2w over m. So 2 multiplied by 62.03844 all over my mass of 17. We get our initial speed of 2.7016. Look at your significant digits very carefully. 2 significant digits, 2 significant digits. This decimal does not count because beforehand is a 0 as well, 2 significant digits. So my final speed must also have 2 significant digits. Therefore, 2.7 meters per second is the initial speed of that curling rock.